Good evening, everyone. Welcome to the sixth discussion hour of the course on robotics, basics, and selected advanced concepts. Last week, we discussed the kinematics of serial manipulators. Specifically, we saw how to relate the joint velocities with the end effector velocities, and we focused on the special matrix called as Jacobian, which relates the quantities in the joint space to quantities in the Cartesian space. We also discussed we also discussed how uh, Jacobian can be computed in different ways. One is to directly uh, take derivatives of the forward kinematics equation, and in another approach, we used velocity propagation, both linear velocity and angular velocity propagation, to find the expression for the end effector velocity in terms of the link lengths and the joint velocities. And yeah, and then we basically concluded that we get the same matrix uh, in both the cases. Now, after that, we also discussed the concept of singularities and basically how we can find out the singular points for a given manipulator by analyzing the Jacobian. So we saw that we can find the determinant of the Jacobian and configurations in which the determinant of the Jacobian is 0. Those configurations correspond basically to the singular configurations. And in singular configurations, serial manipulators lose a degree of freedom, so they cannot move in all possible directions as they can in non-singular configurations. And we usually avoid singular configurations while designing the uh, you know tasks around these manipulators. Now, and then we finally discussed the velocity ellipsoids. So again, we saw that by taking the product of Jacobian transpose and the Jacobian, this special matrix and the eigenvalue and the eigenvector of this matrix basically tells us that in a given configuration, what is the direction in which the end effector can have the maximum velocity for a given angular rate or the joint velocities, and in which direction it has the minimum velocity. So basically, what the manipulability or the velocity ellipsoid tells us is that in a given configuration, what is the direction in which it is easier to move and what is the direction in which it is difficult to move. Now, in this week's discussion, we'll focus on statics. So, firstly, starting from the fundamentals, what does statics mean? So, statics is basically when the rigid body that we are studying, or bodies, as in the case of manipulator, when rigid bodies are at rest, right? They are not moving. So basically, in the case of manipulators, it will be with all joints locked, and then it becomes a structure, right? So a mechanism, so A serial manipulator is a mechanism, and when we lock all the joints and don't allow any motion at those joints, then that mechanism becomes a structure, and the structure has like whatever n members, each member being the link of the of the serial manipulator. So let's say this is the serial manipulator, and we fix this and fix this. We don't allow any motion at these joints, and then what we want to study is that if I apply a certain force at this and a certain moment here, excuse me, then basically what are the torques, joint torques, that are required to sustain those forces. So the problem statement of statics is if all joints are locked, then for a given force and moment, that is torque, on the end effector, what is the or what are the joint torques? So that is the problem that we'll address. That if, let's say, for a 2-hour manipulator, if both the links we are locking them, and then we apply certain force, so basically we are ignoring gravity here, right, in our analysis, and then if we apply certain force and moment on the end effector, then in order to balance, basically we are writing balance equation, force balance and torque balance, and in order to balance those forces and moments on the end effector, what is the joint torque that has to be produced? So basically what we are doing is balance of forces and moments for each link. So what is, so therefore we will use the condition for static equilibrium. Like the condition for static equilibrium is that for a given rigid body, sum of all the forces acting on the body should be 0, and sum of all the moments acting on that body should be 0. So these are the two equations that we'll write for every link, right? So write these two equations for every link in the manipulator. Okay, so let's get started. So before doing our analysis, Let's first establish the notations and what quantities that we will be using frequently in our derivation. So this free body diagram is for a link in that chain of links, right? So the two cylinders at the end are the joints, and in between is the link's body, right? So the first one is the ith joint with axis zi, and then this is the I plus 1th joint axis along zi plus 1. Now the key thing to note here is that these are the two quantities Fi and Ni. So Fi, basically what is Fi? Fi is the force applied on link I, applied on link I by link I minus 1, that is Fi, and similarly Ni is the moment applied on link I by link I minus 1. So Fi and Ni denote this quantity. So Fi plus 1, that would be the force applied on link I plus 1 by link I, and similarly Ni plus 1 would be the moment applied on link I plus 1 by link I. So that's how the convention goes. Then other quantities we have seen before as well. So x, y, z. This is the frame at the ith joint. Xi plus 1, yi plus 1, zi plus 1 is the frame at I plus 1th joint. This vector oi plus 1 is the oi plus 1 is the position vector from the origin of the ith frame to the origin of the I plus 1th frame, and the left side superscripts denote the frame in which these quantities have been expressed. So here I means that this vector has been expressed in the ith frame. Alright, so now on this link there are two forces acting. One is Fi and other is uh, minus of Fi plus 1. Okay, so on this link I'm not drawing the joint separately, just I'm drawing this. So here the forces and this is and this is, so this is link I. So link I experiences a force Fi that is applied by link I minus 1, and this link I applies a force Fi plus 1 on link I plus 1, but it use from Newton's third law, this would experience an equal and opposite of force this. So since I have made the arrow going like this, so here also like it has shown, so this is Fi plus 1, right? So Fi plus 1. Now doing sigma f is equal to 0 for link I, that gives us Fi plus the opposite of the force that link I applies on I plus 1, and the sum is 0 due to static equilibrium. So the equation becomes Fi minus Fi plus 1 is 0, and we can express this in the ith frame itself. Then this becomes like this. So this is the force balance equation, very straightforward, just the application of the static equilibrium equation. Now again, uh, next part is we do sigma m is equal to 0 for link I. Now, what all moments does link I experience about OI minus OI, right? So first there is a moment on link I due to link I minus 1, that is, let's say, Ni. Then there is the opposite of what uh, link I applies on I plus 1, right? So opposite of that. And then due to this application of force Fi plus 1 at a distance OI plus 1, so that creates a moment. So that is the third thing that we need to consider. So the equation becomes Ni, then the reaction torque, or the opposite of what I applies on I plus 1, and also the opposite of what is generated due to the force that is away from the origin of the ith frame. And we can all write this in the ith frame. Okay, so basically what we have is that the moment at the closer to the base joint or the inner joint is the moment due to the reaction and the moment due to the force. Right. So this is the second equation. And we can express these quantities, this moment of applied by I on I plus 1, the force applied on I plus 1 by I, all this we can express in the frames of that body itself. So we will use appropriate rotation matrices. So we can write like I, this is ith force in the ith frame. So that is by doing this conversion. And So here, all the quantities that we use, they are expressed in the same frame as uh, the link for which that quantity is being used. So this is another form that we will use in our static analysis. So the equations are these only. So these are the static force and moment equation. Now, as you would see, in the case of, or if you remember, in the case of velocity, angular velocity and velocity propagation, we started from the base link because there we knew that the velocity is zero, right? So we started from the base link and we progressed outwards in the tree. So that is forward recursion. In case of forces, we do inward recursion because we know the forces that are required at the end effector, and from there we keep on coming in towards the base one link at a time, and we keep on writing these equations at each step. So important point is that force propagation is inward recursion, and velocity was outward recursion. Okay, so now we will finally, we want what we wanted to achieve was the joint torques, right? So the joint torque for the ith joint would be the moment that is there in that joint, and we take dot product with the axis of rotation, right? So this is for rotary joints, and for prismatic joints and this is the prismatic joint. Now what we will do right now is basically solve an example for a 2-hour manipulator, and by the end of that example we would see that in this relation also, the relation between the torques and the end effector forces that are in the Cartesian space, the relation features the Jacobian, right? Shouldn't be a surprise that the Jacobian relates the static equilibrium relation for the manipulators. Okay, so let's get started with the example. let's assign the frames. This is the 0th frame, then this is the first frame, then this is the second frame, and this is the third frame. And the force can be written as F3, and that is, so this left hand superscript denotes that I'm writing F in the third frame, that frame at the end effector, and that is Fx, Fy, and 0. So now for link 2 we write sigma f is equal to 0. So for link 2 the force would be F on 2 expressed in frame 2. Now remember that frame 2 and frame 3 are parallel. Right, there is no change in orientation between these two frames. So F2 is minus this F, which has the same representation in the second frame also. This is equal to 0. So F2 is Fx, Fy, and 0. Now, so we have the force F22. Now this, the moment. So what was the equation for the moment? That this is 0, right? Because we don't have any moment at the end effector, and then we'll just have the second term. So this is F22, and then the length, that is length of the second link. So that is L2 x2 cap, because it's the length is along the x-axis, and that's the force. This is so this is F22, and this leads to we are taking cross product. So x cross x would be 0, x cross y would be z, and this is 0 itself. So there will be only a z component, and that will be L2 Fy. Alright, so notice that we are doing the inward recursion. We started from the tip of the manipulator, and then step by step way we are finding the forces and moments on each of the links and joints in an inward recursion manner. Now what would be the, now we come on to the link 1. So force on link 1 expressed in the first frame. So firstly, force on link 1 this should be minus force on 2 expressed in the first frame. So that is implies that this is equal to R. This is the rotation matrix from 2 to 1, and this is F2. This is so when we multiply this, we get so this is the force uh, that is being applied on link 1 and expressed in the frame 1. And finally, what we need to compute is moment for link 1. So first we'll add the moment, and then it will be L1 x1 and this will be F1 1. And this upon multiplication becomes so what we have is that tau 2 is L2 Fy and tau 1 is L1 S2 Fx plus L1 C2. So this is now if we write this expression in a matrix form, then this becomes L1 S2 L2 plus L1 C2 0 and L2, and this is Fx Fy. So what is this? This is the tau vector, and this is basically the Jacobian of the end effector but expressed in the third frame, and this is the transpose of that, and this is the force in the third frame, right? So this Jacobian matrix and this force, this is a very important relationship. So static equilibrium relation between external forces I will pause here for a minute or so. Okay. So what this relation means is that for the static equilibrium case, the forces on the end effector, and not only forces, it can be forces and moments on the end effector, are related to joint torques by the transpose of the Jacobian. So, if you would see the discussion hour of the previous week, then you would see that this matrix, this 2 by 2 matrix that we have written here and written it as J transpose, is indeed the transpose of the Jacobian when it is expressed in the third frame. So, the key thing to note here is that the same relation can also be written in different frames. So, then the just what you should note is that the frame in which the Jacobian is written and the frame in which the forces are there, they should be always the same frame, must. Then only we will get the correct joint torques. So if we will express the forces, the same forces in the zeroth frame and the same Jacobian in the zeroth frame, then we will get the same joint torques. Now this relation can also be arrived upon uh, using a approach of principle of virtual work. So imagine that argument of structure, that all the joints are locked, and then if the force on the end effector, that is F, and that moves the end effector by a small displacement delta x, then the work done by this force for creating a displacement delta x should be equal to the small displacement that is there in all the joints and the torques at those joints. So this relationship should hold. Now another relation that we will use is that this is equal to Jacobian times this. Okay. Now using this relation here, what we get is F times J delta theta is equal to tau times, this is a dot product, this is a dot product, and we know that A dot B can also be written as A transpose B. So this is F transpose J delta theta, and this is tau transpose delta theta. So this is F transpose J delta theta, and this is tau transpose delta theta. So this implies that tau transpose is equal to F transpose J, and hence taking again the transpose on both sides, tau is equal to J transpose F. So again we see that from the principle of virtual work, for a static case we get this relation. We get the same relation for static equilibrium. And you can do the same analysis for different types of robots. Now what happens in case of singularities? So singularities. So in the case of kinematics, we saw that uh, when the manipulator is in a singular position, then basically it loses a degree of freedom and cannot move in that direction. The same way, uh, in the same way, when a singularity is hit, the manipulator loses the ability to produce forces in certain directions. So you can imagine that for a 2-hour manipulator, when it is in a singular position, that is, it is completely stretched, then it can apply forces uh, in this direction. Here it can apply a force, here it can apply a force, but this direction it cannot uh, it cannot apply forces in so let's verify this. So we know that for a 2-hour manipulator, singular positions occur at theta 2 is equal to 0 and pi. So the Jacobian in frame 3, the tool frame, that is L1 S2 0 L1 C2 plus L2 and L2. Now at theta 2 is equal to 0, J3 is equal to theta 2 is 0, so this is 0 0 L1 plus L2 and L2, right? Now we know that tau is equal to J transpose F, right? So in this case, what we can see is that in the singular case, that is when 0 0 L1 plus L2 and L2, and this is, let's say, the force Fx Fy, then on multiplication this becomes 0 and this becomes L1 plus L2 times Fx, and no, this should be J transpose, right? So this would be transpose. So so it would be 0 0 L1 plus L2 and L2, and then Fx and then Fy. So this would be equal to L1 plus L2 Fy into L2 Fx. Or we can straight away use the yeah, the correct matrix multiplication would be so tau would be L1 plus L2 Fy and L2 Fy. So what we see is that the force along y, this direction, uh, that only plays a role in the torque expression, and in x, uh, the forces in x, they do not appear in this torque equation. So basically these forces, arbitrarily large forces, can be generated with even a small increase in the joint torques, right? So that is the implication for singular position in the case of statics. All right, now this is pretty straightforward. Now the final topic in the agenda today is redundancy. So redundancy is when there are more number of degrees of freedom than more number of degrees of freedom in the manipulator then that is required. So for most, we have 6 degrees of freedom, then we can uh, place the end effector in the arbitrary position and orientation. And if we have more than 6 degrees of freedom in a manipulator, in a general manipulator, then that manipulator is redundant. In case of, let's uh, for a planar case, for a planar case, so a 3R manipulator. So this is a 3R planar manipulator. So this is redundant if if we only consider end effector position x comma y, and this is not redundant if we consider end effector position xy and orientation, that is phi. And so for redundant manipulators, the inverse kinematics does not have a unique solution, does not give a unique solution. So what we do is we add additional constraints. And these constraints can be minimization of joint velocity, this can be collision avoidance, it can be self collision avoidance, it can be obstacle avoidance, and all these constraints can be expressed in form of different mathematical expressions, and then an optimization problem can be formed that gives us a unique solution for the inverse kinematics. So to summarize today's discussion are, what we discussed is the statics for uh, serial manipulators, and how the forces and moments are balanced for each of the link, and basically we get a recursive relation that is processed from the outermost link to the innermost link, and this gives us basically the the forces and moments that are acting on each link. And in terms of the forces and moment of the at the end effector, we finally get the joint torques. So we get the expression of joint torques by taking dot product of the moment at the ith joint with the axis of the ith joint, and we see that the static equilibrium condition between the relation between the forces and the joint torques uh, pictures in the Jacobian matrix. So tau is equal to J transpose F, where tau is the joint torque at each of the joints. Jacobian matrix is uh, expressed in the same frame uh, as the force, the frame in which you are writing the end effector force, that should be consistent, and we do this multiplication to get tau. So when we discuss about the control aspects of manipulator, we will be using this relation very frequently to convert quantities from the from the task space or the Cartesian space to the uh, joint space. And we saw that the same expression also comes up when we use the principle of virtual work to derive the relation between forces and joint torques. And finally we saw that in singular positions, In certain directions, arbitrarily large forces can be applied and generated with very small increase in the joint torques. And finally, we see that for redundant manipulators, uh, we have to include additional constraints which is specific to the task that we want to achieve, which can be minimization of joint velocities, self collision avoidance, obstacle avoidance, or moving the end effector in a very specific uh, motion. All these constraints can be included to put restrictions on the number of solutions that are valid and to get a unique solution. So, this is what I had planned to discuss in this discussion hour, and we'll discuss continue our discussion in the next discussion hour. Thanks for joining.